Hi, this is Stu Schwartz from MasterMathMentor.com. This is video Precalc 05A, and the topic is Analytic Trigonometry. In algebra and trigonometry, there are three terms that are sometimes used interchangeably. However, they are not the same. They have a certain similarity, but they are quite different. The first is an equality. An equality is a statement that is always true. For example, 2 is equal to 2, 3 plus 4 equals 7, 6 squared equals 36, 2 times the quantity 3 plus 5 is 6 plus 10. The sine of 270 degrees is equal to -1. These statements are always true. They can never be false. Equations are slightly different. Equations are statements that are conditionally true, depending on the value of a variable. For instance, 2x plus 3 is equal to 11 is true only if x equals 4. Quantity x minus 1 squared equals 25 is only true when x is equal to 6 or -4. X cubed minus 2x squared plus 5x minus 12 equals 0 may have up to 3 solutions. We'd have to check it out on the calculator to see. 2 cosine theta is equal to -1 only when cosine theta is equal to -1/2. And we know that there are an infinite number of values of theta for which this is true. Inverse tangent of x is equal to 2.5 will definitely have solutions. We'd have to check it on the calculator to find them. An identity is an equation that is always true, no matter the value of the variable. 2x plus 3x is equal to 5x is always true. It does not matter what x is. For quantity x minus 3 is always equal to 4x minus 12. Quantity x minus 1 squared is equal to x squared minus 2x plus 1. Again, the value of x does not matter. And 1 over x minus 1 minus 1 over x plus 1 is equal to 2 over x squared minus 1. This too is an identity, and you can show this algebraically. In the last example, it could be argued that this is not an identity because it is not true for all values of the variable. X cannot be 1 or -1, as it will make denominators equal to 0. However, when such statements are written, we assume that the domain of the expressions are taken into consideration, although we don't always write it. So a better definition of an identity is a statement that is always true for all values of the variable within its domain. A trig identity is the same as an algebraic identity, except it uses trig statements. There are 8 fundamental trig identities that you must know backwards and forwards. We will detail them, but they are all based upon our basic definition of our trig functions, as shown by the graph in the first quadrant. We have a typical triangle with sides x, y, r. The triangle is right, and the angle made with the x-axis is called theta. The first 3 identities are called the reciprocal identities and are true for any value of theta within the theta's domain. First is cosecant theta is equal to 1 over sine theta, secant theta is equal to 1 over cosine theta, and cotangent theta is equal to 1 over tangent theta. This is no great revelation. We do this when we were graphing the cosecant, secant, and cotangent functions on our calculators, as our calculators did not have any way of writing specifically cosecant x, secant x, and cotangent x. We will provide proofs of these statements. 1 over sine theta is equal to 1 over y over r, as looking at the triangle to the left. We take the reciprocal of y over r, which is r over y, and that is cosecant theta. Similarly, 1 over cosine theta is equal to 1 over x over r, which is r over x, which is secant theta. And 1 over tangent theta is 1 over y over x, which is x over y, which is the cotangent theta. The next two you have not seen before, or at least formally. They are called the quotient identities. Tangent theta is equal to sine theta over cosine theta, and cotangent theta is equal to cosine theta over sine theta. We again prove this using our picture. Sine theta over cosine theta is y over r over x over r, and multiplying both numerator and denominator by r, we get y over x, and that by definition is tangent theta. Similarly, cosine theta over sine theta is x over r over y over r, and when we flip, we end up getting x over y, and that is cotangent theta. The final three are called the Pythagorean identities. Sine squared theta plus cosine squared theta is equal to 1. 1 plus tangent squared theta is equal to secant squared theta, and 1 plus cotangent squared theta is equal to cosecant squared theta. We prove these statements somewhat differently. In all cases, we start with the Pythagorean theorem, based upon our picture, x squared plus y squared equals r squared. We divide each term by r squared, and we get x squared over r squared plus y squared over r squared is equal to r squared over r squared. And that gives us cosine squared theta plus sine squared theta is equal to 1. When we memorize this, we tend to say sine squared theta plus cosine squared theta is equal to 1. Next, we start with x squared plus y squared is equal to r squared, and divide each term by x squared. When we do that, we get 1 plus tangent squared theta is equal to secant squared theta, our second identity. And our third example, starting with the Pythagorean theorem, we divide each term by y squared. And we end up getting cotangent squared theta plus 1 is equal to cosecant squared theta. Just as you did with the basic trig functions, it is vital to memorize the 8 fundamental trig identities, as you will use them over and over again. Do what you need to do to memorize them. Make flashcards or write them down and have someone test you, but it is important that you know them backwards and forwards. A corollary is an identity that is also true because one of the 8 fundamental trig identities is true. While it is important to memorize the 8 fundamental trig identities, it is not necessary to memorize the corollaries, although you will use them so often that you end up memorizing them whether you like it or not. For instance, because cosecant theta is equal to 1 over sine theta, then sine theta cosecant theta is equal to 1, and sine theta is equal to 1 over cosecant theta. The same type of reasoning can be done with cosine and secant. Cosine theta secant theta is equal to 1, and cosine theta is equal to 1 over secant theta. And the same reasoning is true with the tangent and cotangent functions. Tangent theta cotangent theta is equal to 1, and therefore tangent theta is equal to 1 over cotangent theta. For the quotient identities, cross-multiplying, we get tangent theta cosine theta is equal to sine theta, and therefore sine theta over tangent theta is equal to cosine theta. Or cotangent theta sine theta equals cosine theta, and therefore cosine theta over cotangent theta is equal to sine theta. For the Pythagorean theorem identities, there are more corollaries. We will just work with the first one, sine squared theta plus cosine squared theta is equal to 1, as we tend to use that the most. We can separate our terms and write cosine squared theta is equal to 1 minus sine squared theta, or sine squared theta is equal to 1 minus cosine squared theta. And then for each, taking the square root of both sides, we get that cosine theta is equal to plus or minus the square root of 1 minus sine squared theta, and sine theta is equal to plus or minus the square root of 1 minus cosine squared theta. As mentioned, you can do the same manipulations with the second and third Pythagorean theorem identities. In this section, we are given a number of trigonometric identities. Now remember, identities are true. Our job here is to prove that they are true. Our tools will be the knowledge that we have of algebra, using the 8 trig identities, and also your ingenuity. Some of them will be easy, and some are a little bit more difficult. Let's take a look at 2 examples. In both problems, we are to prove that the left side of the equation is equal to the right side of the equation. In number 1 for all values of theta, and in number 2 for all values of x. That's what makes it an identity. There are a number of guidelines that we use to verify these trig identities. The first is that we need to prove that one side of an identity is equal to the other, so you only work on one side of the identity. And you always work on the most complicated side and try to transform it to the simpler side. When we say more complicated, the side is longer, has more complicated expressions. We consider addition or subtractions more complicated than multiplications. In number 1, we have to show that sine theta times the quantity cosecant theta minus sine theta is equal to cosine squared theta. We obviously work on the left side. It is more complicated than the right side. And we will multiply out our expression to write sine theta, cosecant theta, minus sine squared theta. We use the fact that cosecant theta is 1 over sine theta. That is identity number 1 in our reciprocal identities. And so we have sine theta times 1 over sine theta minus sine squared theta. We get cancellation and we are left with 1 minus sine squared theta. And 1 minus sine squared theta is equal to cosine squared theta. That is a corollary of one of the Pythagorean identities. We have shown what we need to show. Number 2 is much harder. We have to show that secant squared x over tangent of x is equal to 1 over sine of x cosine of x. We say that expressions that have tangent, secant, cosecant, or cotangent as expressions that are more complicated than those that have sine and cosine. So we will write the left side as secant x times secant x over tangent of x. The first secant of x we will keep, but we will write secant of x as 1 over cosine of x and tangent of x as sine x over cosine x. We have a complex fraction, and therefore we can flip the denominator and write this as secant x times 1 over sine of x. But secant of x is 1 over cosine of x. So we have 1 over cosine of x, sine x, and we have proved what we need to prove. This is more complicated. I showed you one of the harder ones. What we need to do is come up with some generalizations about how to tackle these problems. Here are some generalizations that you can use to verify trig identities. Some will work on certain problems, others will work on other problems. Number 3, if an expression can be multiplied out, then do so. We saw that on problem number 1. Number 4, if a problem can be factored, do so. Number 5, if you have a polynomial that is written over a single term, we can split it into several fractions. Number 6, if you have an expression that involves adding fractions, do so by finding a lowest common denominator. Number 7, when in doubt, convert everything to sines and cosines. We saw that in problem number 2. Number 8, don't be afraid to create complex fractions. Once you do that, many problems are a step away from solution. Again, we saw that in problem 2. And number 9, always try something. You don't have to see the solution before you actually do the problem. Sometimes when you try something, the solution just evolves. And if you try something and it doesn't seem to be heading anywhere, then try something else. In problems 3 through 8, we have 6 identities to prove of varying difficulty. Difficulty is usually rated in terms of the number of steps that is needed to prove the identity. Some can be done in a matter of 2 steps. More difficult ones can take 4 or 5 steps, and very difficult ones can take 10 or more steps. Here we have some simple ones and some medium difficulty ones. In number 3, we have to prove that sine x times the quantity cosecant x plus sine x secant squared x is equal to secant squared x. First, it is clear we're going to work on the left side. It is obviously more complicated. And we're going to use our guideline that we're going to multiply out our expression. So we have sine of x, cosecant of x, plus sine squared of x, secant squared of x. Next, we will use our guideline that when in doubt, change things to sines and cosines. So we have sine of x times 1 over sine of x plus sine squared of x times 1 over cosine squared of x. In the first fraction, we get cancellation and we are left with 1 plus sine squared of x over cosine squared of x. At this point, you have to realize that sine squared over cosine squared is tangent squared, and we're left with 1 plus tangent squared of x. And at this point, you must recognize that this is an identity, that 1 plus tangent squared of x is equal to secant squared of x. You should always look on the right side of the equation as well to see what it is you are trying to prove. When I gave tests on proving identities, every once in a while I would get a student who would show the solution in 2 steps. While the first step is clear, the second step isn't, and I would give the student very little credit for the problem. Frequently, the student would argue by saying, I proved it. I ended up with secant squared of x. When I said that it wasn't clear how he arrived at that, he said, well, he just did the work in his head. Most of the time, that student was trying to snow me. But I point out that the goal of these problems is to show the logic in arriving at the right side. Steps should be clear and easy to follow. And if you do too many steps at once, the logic frequently disappears. When in doubt, show the steps. Number 4 asks us to prove that 2 cosine squared of x plus sine squared of x is equal to cosine squared of x plus 1. Again, we choose to work on the left-hand side of the equation because there are 2 trig functions on the left side as opposed to just one on the right. We write 2 cosine squared of x as cosine squared of x plus cosine squared of x plus sine squared of x, and realize that cosine squared of x plus sine squared of x is equal to 1. And therefore we have cosine squared of x plus 1, and we're done. This is an example of a very easy identity, and one that just sort of evolves. If you do something, you end up getting the right answer. In number 5, we have to prove that 2 cosine squared of x minus 1 is equal to 1 minus 2 sine squared of x. It is not clear which side is more complicated, so we choose the left side to work on. When we do that, always keep one eye on the right side. If we work on the left, we need to change cosine squared to sine squared. Luckily, we have an identity, actually a corollary that does that. Cosine squared of x is 1 minus sine squared of x. So we have 2, quantity 1 minus sine squared of x minus 1. And when we multiply out, we get 2 minus 2 sine squared of x minus 1, and that leaves us with 1 minus 2 sine squared of x. In number 6, we have to show that sine of x plus cosine of x quantity squared plus sine of x minus cosine of x quantity squared is equal to 2. This is a problem that looks hard, but is remarkably easy. Obviously, we will work on the left-hand side of the equation. And since we have expressions that can be multiplied out, we will do so. So we have sine squared of x plus 2 sine x cosine of x plus cosine squared of x plus sine squared of x minus 2 sine of x cosine of x plus cosine squared of x. The 2 sine x cosine x cancels, so we are left with sine squared of x plus cosine squared of x plus sine squared of x plus cosine squared of x, and each of these, sine squared of x plus cosine squared of x, is 1. So we have 1 plus 1, and we get 2. In number 7, we have cotangent of x over cosecant of x is equal to cosine of x. Here we will use our guideline to change things to sines and cosines. So we have cosine of x over sine of x over 1 over sine of x. We create a complex fraction, and you can't be afraid to work with them. We simply flip the denominator and multiply, and we're left with cosine of x over sine of x times sine of x over 1, and the sine of x is canceled, and we are left with cosine of x. Number 8 reads tangent of x plus cotangent of x is equal to secant of x cosecant of x. We again will choose to work on the left-hand side of the equation because additions are considered more complicated than multiplications. And we will use our guideline to change to sines and cosines. So we have sine of x over cosine of x plus cosine of x over sine of x. Since we are adding two fractions that have different denominators, we will get a common denominator, which is sine of x cosine of x. We multiply our first fraction by sine of x over sine of x, and our second fraction by cosine of x over cosine of x. And we are now left with sine squared of x plus cosine squared of x over sine x cosine of x. However, we realize that sine squared of x plus cosine squared of x is 1. So we can now split the denominator and write this as 1 over sine of x times 1 over cosine of x, and we are left with cosecant of x, secant of x, which is what we are trying to prove. In problems 9 through 14, we continue with proving identities, with some of these problems a little bit more difficult. One of the conventions we use in proving identities is we choose a side to work on and then work downward. In several of these problems, I choose to violate that convention because of space considerations. Number 9, we have secant of x minus cosine of x equals sine of x tangent of x. The left side is more complicated because of the subtraction. We write secant of x as 1 over cosine of x minus cosine of x. Here is an example of a subtraction where we have two fractions, one with a denominator of cosine of x and the other with a denominator of 1. We need to get a common denominator, so we will multiply the second fraction by cosine of x over cosine of x, and we are left with 1 minus cosine squared of x over cosine of x. However, 1 minus cosine squared of x is sine squared of x. You must recognize that, and we are over cosine of x. Now this is where you have to look at the right-hand side. We want to get a sine x tangent of x, so we realize that we can split sine squared of x into sine x sine of x. So we end up with sine of x times sine x over cosine of x, which is sine x tangent of x. In number 10, we have sine of x plus cosine of x, cotangent of x, equals cosecant of x. Obviously, we work on the left side. We will first change to sines and cosines to get sine of x plus cosine of x times cosine of x over sine of x. And we can then multiply out to get sine of x plus cosine squared of x over sine of x. Here again, we are adding two fractions with different denominators. We need a common denominator, and we multiply the first fraction by sine of x over sine of x, and we end up with sine squared of x plus cosine squared of x over sine of x. From here it is easy. Sine squared of x plus cosine squared of x is 1 over sine of x, and we get cosecant of x. 11 reads cotangent of x plus 1 over cotangent of x minus 1 is equal to 1 plus tangent of x over 1 minus tangent of x. This problem looks difficult, but it's actually quite easy. You may want to think about changing to sines and cosines, but if we work on the left side, we realize that we need to go from cotangents to tangents, and we have an identity that does that. So we will write cotangent of x as 1 over tangent of x plus 1 over 1 over tangent of x minus 1. We have a complex fraction. And to eliminate a complex fraction, we will multiply both top and bottom by the LCD. So we will multiply by tangent of x over tangent of x. And when we multiply out, guess what? We left with 1 plus tangent of x over 1 minus tangent of x. Exactly what we were trying to prove. Number 12 reads secant squared of x minus 1 over secant squared of x is equal to sine squared of x. We obviously work on the left-hand side, but what do we do? This problem uses one of the generalizations we showed that says that when you have a polynomial over a single term, you can break it up into several terms. So we will write each term over secant squared of x, and we get secant squared of x over secant squared of x minus 1 over secant squared of x. Secant squared of x over secant squared of x is obviously 1, and we're left with 1 minus 1 over secant squared of x. But using the corollary to identity number 2, we have 1 minus cosine squared of x. And realize that we have now the corollary of the Pythagorean identity. We are left with sine squared of x. Frequently, there is more than one way to prove an identity. Instead of splitting this into two fractions, we can use the fact that secant squared of x is 1 plus tangent squared of x, minus 1 over secant squared of x. The ones cancel. We're left with tangent squared of x over secant squared of x. Changing everything into sines and cosines, we get sine squared of x over cosine squared of x over 1 over cosine squared of x. And we can now multiply both top and bottom by cosine squared of x, and we end up with sine squared of x. Just about the same amount of work. 13 reads 1 over 1 minus sine of x plus 1 over 1 plus sine of x is equal to 2 secant squared of x. This problem is an example of a situation where you follow general guidelines, not seeing where it's going to lead. And sometimes the answer just evolves. What we first do is get a common denominator, which is 1 minus sine of x times 1 plus sine of x. So we will multiply the first fraction by 1 plus sine of x over 1 plus sine of x, and the second fraction by 1 minus sine of x over 1 minus sine of x. So we now are left with 1 plus sine of x plus 1 minus sine of x over our LCD, 1 minus sine of x, 1 plus sine of x. In the numerator, the sine of x's cancel, and we're left with 2 over 1 minus sine squared of x. Realize, though, that 1 minus sine squared of x is cosine squared of x. And this is where you look at the right-hand side of the equation and realize that 2 over cosine squared of x is 2 secant squared of x. Number 14 reads cosecant of x plus cotangent of x over tangent of x plus sine of x is equal to cotangent of x cosecant of x. Obviously, we will work on the left-hand side. This is one of those problems where you just follow guidelines and hope that things will work out. Our first guideline we will follow is change everything to sines and cosines. So we have 1 over sine of x plus cosine of x over sine of x over sine of x over cosine of x plus sine of x. We eliminate the complex fractions by multiplying everything out by the LCD, sine of x over cosine of x over itself. When we do that, we get cosine of x plus cosine squared of x over sine squared of x plus sine squared of x cosine of x. What to do now? Well, we see that up top we can factor out a cosine of x. So we have cosine of x times the quantity 1 plus cosine of x. On the bottom, we can factor out a sine squared of x. And we have sine squared of x times 1 plus cosine of x. We know that things are heading in the right direction because the 1 plus cosines of x cancel. So we are left with cosine of x over sine of x times 1 over sine of x. And that gives us exactly what we want, cotangent of x, cosecant of x.